Can you hear me? You feel free to unmute and, yeah, Raina, go ahead. Okay. All right.
Yes, madam, we can hear.
Okay. Thank you, Shivantika. Okay, so we can start off now. Um, the other students can then join us later on, right? So, hello everyone. Hi, students. Welcome to Unifiji's ER 13 physics tutorial session, right? So, my name is Drishna Charan, and I take physics at the university, right? So this is a 1 hour session. I'll be taking the first half an hour of this session, and then Mr. Melvin Nathan will be taking the second half of this session, right? So let's get started. What I'm going to do right now is I'm going to share my presentation, and then we can work on that presentation together. If I have questions, I'll ask you, you'll tell me. If you have questions, do let me know, put it in the chat box, and if we have time, then we can go on to answer any of the questions that you have, right? All right. So let me start presenting my screen now. Okay. All right. So I hope you can see my presentation. Shivantika, can you unmute and let me know quickly? So I'll just start off. Can you see the presentation on your screens now? The PowerPoint presentation.
Yes, madam.
Okay, great. All right. Right. So generally, whenever you do any physics course, we have a set of different sections that need to be covered, right? So if you talk about physics, we start off our study of physics. We start off by looking at classical mechanics, right? So essentially, what we do is we look at objects, how these objects are moving, where they are moving, what is the velocity with which they are moving, what energy does it have, for example, what is the momentum through which it is moving, right? So these are some of the things we try to answer in the topic of classical mechanics. Then you go on to looking at things that wave, right? So we look at essentially waves. So under waves, you look at different types of waves, such as sound waves. We have water waves. We also have, for example, waves on a string, right? So which essentially oscillate. And then we go on to look at electrostatics. In electrostatics, what we look at is we look at charges which are stationary. Then we go on to look at electricity, DC circuits, and that is what I'm going to be covering today. Right, so I'll be looking at the topic DC circuits exclusively. Now, after DC circuits, you would be looking at, in your studies, you must have obviously covered magnetism, and then combine electricity and magnetism together, you get electromagnetism, and then you finish your studies off with quantum, modern physics or quantum physics, right? So, looking at your past examiners' reports, we feel like the topics that we need to concentrate on and that will help you to prepare for your final exams better is electricity, magnetism, and electromagnetism. Right, so I am taking electricity. So essentially, I'm going to be talking about charges which are moving. And then my colleague, Mr. Melvin, he will be looking at the topic of electromagnetism, right, under which he'll talk about Faraday's law and Lenz's law and so forth. So essentially, what am I going to cover? Okay, so the topics that I'll be looking at is current, right, resistance, power, and then how you can use all of these three to essentially solve a DC circuit. Right, so these are the things that I'll be looking at. So I'll quickly go over some of these concepts with you. And if you have any questions, do let me know. Right, so I'm starting off with talking about electric current. We know what electric current is, right? We use the symbol I in order to denote it, and the unit that we use for electric current is amps. whereby 1 m is equal to 1 coulomb per second. Now, what precisely is electric current? Right. So essentially, whenever we apply a potential difference across a resistor, across a conductor, for example, this potential difference causes an electric field to be established, right? So let's get that again. A particular potential difference applied across the ends of a conductor causes an electric field to be established. And this electric field pushes, right, or causes rather the charges to start moving. The positive charges move in the direction of the electric field, whereas the negative charges move in the opposite direction of the electric field. And this is where current comes about. So whenever we have charges moving, current comes about. Whereas current is simply the rate of flow of charge through some region of space. Right? So for example, you have a diagram over here. This shows you the cross section of a wire. So just imagine I have a pen in front of me, right? I hope you can see it. So if this is a wire, for example, this, and you have essentially electrons or charges flowing through it, this represents its cross-sectional area. So if we want to find out what is the current which is flowing across this wire, it is simply going to be the rate at which this charge is changing per time, or essentially how many charges are passing through each second. So that is what electric current essentially is. Now, we've defined electric current simply as the rate at which charge is flowing per time. So let's say we have an equation for charge given, and let's say this charge keeps on changing, varying with time, right? So that means the charge doesn't stay same, it varies with time. Now it varies according to the equation which is shown on the slide, right? So this is a problem question for you. Q is equal to 4t cubed plus 5t plus 6. So that means charge keeps on changing, keeps on increasing per time. If you want to know what the charge is, let's say at time t is equal to 1 second, you'll put down t in place of t, you'll put down 1. If you want to know what the charge is at 2 seconds, you'll put down in place of t, you'll put down 2 at this location. Right. Now let's look at what the question is asking us. What is the instantaneous current through the surface at time t is equal to 1 second? So my question to you is, let's start off with the question. If we have an equation for charge and we see that charge is varying per time, from that equation of charge, how can we get an equation for current? Anyone? You can type it in the chat box if you wish, or you can unmute yourself and speak to me. Anyone wants to give it a try? No? Okay, let me tell you. So essentially, in order for us to get an equation for current from an equation for charge, we simply differentiate it, right? Because essentially current is the rate at which charge is changing per time. So let me just quickly do that for you here. So current will simply be differentiating charge with respect to time, right? So if we are looking at current, for example, over here, right? Let's differentiate this equation for charge. We differentiate it, 4t cubed becomes 12t squared, right? So I've differentiated the first term. Let me differentiate the second term. So 5t simply becomes 5. Plus 6 if you differentiate it becomes 0. So that's fine as well, right? So the equation for current is 12t cubed plus 5. So we know how current is going to be changing. So now let's find out what the current is at time t is equal to 1 second. What would you do? You simply substitute the value for t as 1 in this equation. So let's do that. You'll have I is equal to 12, right? We put 1 in place of t and then squared plus 5. What do we get? We get a value of 17 amps. So this is the value for current at time is equal to 1 second. What about at 5 seconds? What will you do then? You'll simply put down in place of t, you'll put down 5, right? And then calculate what the value for current is. So that is how we get, if you have an equation for charge, we can find an equation for current simply by differentiating it with respect to time. Right. All right. Now, let's look at another equation over here. So I've broadly described to you what current is, and sometimes it helps us if we take a microscopic view of it as well. So let's say, remember if we want charges to move, what do? We apply a potential difference across it. You insert a battery, you put an external power supply across a conductor, for example, across a resistor. And again, the process causes the electric field to be established, which pushes the charges, right? Causes charges to move. So let's say we have these charges, and these charges are moving through a particular conductor, and as usual, this conductor has a cross-sectional area A. Now, we often call these charges charge carriers, right? So for example, we call an electron a charge carrier, which is carrying a charge of 1.6 times 10 to the power of negative 19 coulombs. Right? So now if we want to investigate what is the current which is moving through a conductor, we can use this formula. Right? This tells us that that current is dependent upon, first of all, it depends upon how much charges there are in a particular space, which is represented by N. N over here represents the charge density, or rather the number of charge carriers per unit volume. The other thing that this current depends upon is Q, which is the charge. If you're looking at electrons, we can change this to Ne, right? Instead of Q, we can write down E. E over here refers to electronic charge. Then we have V. V refers to the drift speed, and I refers to this cross-sectional area that I had explained to you before. So essentially, the reason why I wanted to introduce this formula is because it's very important for our understanding of other things. One of the things that I want to discuss about here is the drift speed. What is this drift speed? Now, when these charges are moving, when the charges start to move, they're not going to be moving just straight forward, right, in a straightforward direction, or just continuously forward in the forward direction. No. Why? Because as these charges are moving, they are going to collide with the atoms of the conductor, right? So instead of just a forward direction, they'll be colliding with atoms of the conductor. So they'll move they'll collide with the atoms, they move up somewhere else, for example, they'll start moving again collide. So in that way, the forward movement of these electrons is very slow, and that is why we call it the drift speed. We can use this equation in order to calculate what is the current which is moving, or what is the average current through a conductor. There's another important equation, I'll just introduce it, and that is the current density. Current density is a term, right? Again, we can use in order to find out the density of current, and it is usually found out by the formula, the amount of current divided by the cross-sectional area which it is moving through. Right. Now, after current, let's have a look at resistance. So again, we are connecting a conductor, a resistor across a potential difference, right, causing the charges to move. And like I mentioned, they are going to be colliding with the fixed atoms inside the conductor. And this gives rise to resistance, right? It gives rise to resistance. The units of resistance is ohms, right? We can find out what the resistance is by using the Ohm's law, which is simply potential difference divided by the amount of current which is moving through that particular resistor. Now, let me ask you a few things. What is this resistance dependent upon? What is the value of resistance? Or what factors influence the resistance values of let's say, different conductors. Start this. Let's go back to our discussion. Let's see if anyone wants to speak now. What are, yes, exactly. Thank you, Ayush. It's the temperature. Right? Temperature is one of the things that affect resistance. Anyone else wants to give it a try? There are other factors which affect the resistance of a conductor as well, apart from temperature. You see exactly. Not the yes, cross-sectional area, length, right? So we're getting a lot of answers here. We're getting area, we are getting length, and we got temperature. Precisely. Those are the things that affect resistance. What do we know about resistance and its relationship to all these parameters? Well, first of all, let me just get this pen, start it up, right. We know that the resistance depends upon, first of all, it depends upon the resistivity of the material, right? Whatever conductor you are using. Are you using copper, for example? Are you using silver? What are we looking at, right? So it depends upon the resistivity of that particular material, right? And essentially what the resistivity of a conductor is solely depends upon what that material is made up of. And yes, somebody had correctly identified it. The resistivity also depends upon temperature, and therefore the resistance depends upon temperature as well. So the resistance depends upon the resistivity, which depends upon temperature. The other thing correctly identified is that it depends upon length as well, so that if you increase the length, the resistance will increase. So for example, if you have a resistor of a certain length and you double the length, right, or if you have a conductor which has, let's say, a certain resistance and you double the length of that conductor, the resistance will increase by 2, right? Now, someone correctly identified it is also related to area. In fact, it is inversely proportional to the area, such that if you increase the area, the resistance value will decrease. Right, so if we put that all together to get a formula for resistance of a conductor as rho L upon I. Right, it's very important. Different conductors will have different values for resistance depending upon what it is made up of and what temperature it is, as well as its geometry. Right, so with those concepts of currents and resistance in our belt, let's look at electrical power. Right, what is electrical power? What do we mean by this term? So what you can see on your slide is a very simple circuit. Okay, it's a very simple circuit. What do we have? We simply have a battery over here. We have a switch, and then we have a resistor which is connected across it. Right? Now, in order for us to explain what power is, we need to understand what kinds of energy transformations are going to take place as the charge moves. Right? In this case, the current is directed clockwise, so like you can expect and this is the direction in which the current will be moving. So let's talk about electrical power, or whatever power is going to be delivered to the resistor over here. What's going to be happening? So just imagine a charge, right? A charge is moving. A charge, let's say it moves from point A to point B. Right? Let's say it starts from here, right? Somewhere over here, starts from here. It moves to point A, right? And then it moves to point B. So in doing so, it's going across the battery. Right? So when it moves across the battery, there's going to be a conversion. It is going to, the electric potential energy of the system is going to increase. And at the same time, the chemical energy within the battery is going to decrease. See, this is all a conservation of energy type of situation, right? Whereby whenever we have decrease in chemical energy, that is, therefore there will be, it will be balanced off rather by an increase in electric potential energy. So the electric potential energy of this system increases. Let's say the charge continues on its way. It comes here. It goes across this resistor now, right? So as it's passing across the resistor, these charges are again very important for us to know. They are going to be colliding with the atoms of the resistor. Right? It's going to collide with the atoms of the resistor, and as a result of that, you can expect the temperature of that resistor to increase. The internal energy of the resistor increases as well. Right? So you have an increase in the internal energy of the resistor due to a decrease in the electric potential energy of the system, since the charges are going to be colliding with the atoms. So this power over here represents the rate at which, this power is energy equal to time. This power over here represents the rate at which the electric potential energy of the system is decreasing, and the rate at which the internal energy of this particular resistor is increasing, and that is given by the formula VI, right? So we have delta V, potential difference across this battery, multiplied by the amount of current which is passing through. You'll help remember the derivation of this formula. If you remember that electric potential energy is simply given as delta V Q, right, whereby Q refers to charge. So this is the electric potential energy formula divided by T. And just like we've learned a few minutes ago, the rate at which charge is changing per time, that is current, right? Current is defined as the rate of change of flow of charges rather per time. So this is what the equation becomes. And by using Ohm's law, we can find out the other two equations for power as well. Now, which other two equations do we have? So we have power is equal to I squared R, and we have power is equal to delta V squared divided by R. Right? So these are the three equations that we can use. Now, based on these three equations, there's another question for you. Let's see. You have two conductors of the same length and radius, and they are connected across the same potential difference. So this is same, right? Potential difference is same. One conductor has twice the resistance of the other. To which conductor is more power delivered? Right? Is more power delivered to a resistor which has a smaller resistance, or to the resistor which has a larger resistance? What do you think? So you can just answer it in terms of whether it's going to be a smaller resistor or whether it's going to be a larger resistor. Let's see. Okay. One has a larger resistance, one has a smaller resistance, right? One has a larger resistance, one has a smaller resistance. To which is more power going to be given? Okay, I'll give you a hint. You can use, okay, I think I got one answer over here. Let's see. Larger, well, there's 50% of you getting this answer right, but unfortunately it's not the larger one, it's the smaller one. Why am I saying that? Because just if you put 2R, for example, in this place, you'll see that the power reduces by half the amount for the larger resistor. As you can see, we are not talking about current in this equation. We have not introduced current, so let's not complicate. Let's just look at a relationship between power, potential difference, and resistance, because that is what the question is asking us. So essentially, we are going to be using power is equal to potential difference squared divided by R. So it's inversely proportional according to this equation if we keep the potential difference constant. And therefore, to which conductor is more power going to be delivered? It's going to be the smaller resistor. A larger resistor would mean lower power. Right. So let's have a look at DC circuits, right? DC circuits. What are DC circuits? Essentially circuits in which the value or rather the direction of current does not change. It stays the same. You have situations or circuits in which current keeps on changing. What is that? That is an example of an AC circuit. Right? So what we are going to look at now is using all the ideas that we've learned about resistance, about current. Let us just look at DC circuits. How do we solve DC circuits? Right, so essentially you do know about certain laws. For example, if resistors are connected in series, you simply add them up, right, or interconnected in parallel, then 1 upon total resistance is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so forth. So using those kinds of equivalent resistance, we can solve many circuits. But sometimes the circuits are a bit more complicated to solve, and that is when we start to use Kirchhoff's laws. There's two laws for Kirchhoff's. First is the junction rule. The next one is the loop rule. So what I'll do is I'll briefly go over these two rules, and then we can do a problem question based on that, right? So for the junction rule, the first law, Kirchhoff's first law, which is the junction rule, it simply states that the amount of current entering a junction is equal to the amount of current which is leaving a junction. It is as simple as that. It comes about due to the conservation of charges. There's not going to be an accumulation of charges at the junction. There's not going to be a depletion of charges at the junction. No. The total amount of charges that come at this junction will be equal to the amount that leaves. So we are going to say that the amount of current, right, the current entering a junction is equal to the amount of current which is going to leave the junction, right, sum of the currents. So in this particular situation, it is simply going to be amount entering is I1, amount of current which is leaving the junction is I2 plus I3. So this is your first equation, right? So what we can do is we use the junction rule to form our first equation towards solving our DC circuit, right? And then we go ahead and look at the second rule, which is known as the loop rule. Now the loop rule is simply a statement of conservation of energy, which states that the sum of potential difference across all the elements across any closed circuit loop must be equal to 0. And this is how we express it mathematically. That is, the sum of all the potential difference across a closed loop is equal to 0. So let me just go back to our problem question and tell you what that means. That means if we can divide this particular circuit into two loops. This is the first loop. That means if we add all the potential difference across all of these circuit elements, add it, sum it up all together, it should be equal to 0. See, some of these cases, according to the direction in which we are moving, some of the potential difference terms are positive, some are negative. According to the loop rule, add it all together in one loop, it should be equal to 0. Right? So how do we know which do we take as a positive potential difference and which do we take as negative potential difference? Well, it depends upon how we are moving. So let's say we are moving from A to B. In all of this situation in which I'm going to explain it, we are always moving from A to B. So what do we have? We have a resistor over here, right? And then we have current which is going past that resistor. So we know there is going to be a voltage drop across this resistor as the current moves past. If you use, for example, a voltmeter, you'll be able to see that there's a voltage across this resistor, a voltage drop. So essentially, as you are moving from A to B, right, this point is going to be at higher potential according to this point, right? This point again, this point over here before the resistor is going to be at higher potential. This point is going to be at a lower potential because that appears across the resistor as a voltage drop. So if we are moving in the same direction that the current is flowing past as well, so if I'm moving from A to B, the current is also moving in that direction, we will take the potential difference across it as negative IR. I over here will represent the current which is passing through that resistor, and R represents the value of that resistor, resistance value of the resistor. So we'll be taking that as negative IR. So why are we doing that? Because we are moving from an area of high potential to a area of low potential. That is why we are taking that as negative IR. Now again, we are in this case, we are moving from A to B, but the current is moving from B to A. Right? It's moving in the opposite direction to which we are moving. Right? So let me just remind you, there is going to be a voltage drop across this, and this area, this particular portion is going to be at a higher potential, and this area, this point is going to be at a lower potential. So as we are going from A to B, we are going from a lower potential to a higher potential. And that is why we are going to be keeping delta V as positive IR. A easy way to remember this is, if the current is moving in the opposite the direction in which you are moving, then you keep that as positive. If the current and the direction in which you are moving is the same, then you keep that as negative IR. But I think it is also very important you understand why we are keeping it as positive and why we are keeping it as negative. So that is one circuit element. If we have resistors, we also have batteries connected across DC circuits. What about those? What are we going to keep those as? Right. So for example, again, this is the direction in which I'm moving from A to B. So as I'm moving from A to B, if I encounter the negative terminal of the battery first and then the positive, we will keep that as a positive electric potential. Why? Because we are moving from a lower potential to a higher potential, right? So we'll keep that as positive. But if you're moving from a higher potential to a lower potential, then obviously we keep that as a negative. Right, so we've learned about these 4 rules that we can use, right? 4 rules which we can use in order to form equations using the loop rule, and 1 equation which we can form using the junction rule. So how does Kirchhoff's law work, right? First of all, you use the junction rule to form 1 equation, and then you use the loop rule to form 2 equations. Right, if there are 2 loops, for example, and then you solve it, right? All right, so this is our problem question here. Let's try this out, right? We have a circuit, we have around 5 resistors in that, and we have around 2 batteries, 4 volts and 12 volts, right? All right, so what I'm going to do is I'm going to quickly switch to solving this on the whiteboard. All right, so it's the same question, right? I've just pasted it right over here. Now let's solve it. The first thing that we'll use is the junction rule. Junction rule will give us equation number 1, right? So give me 1 minute here. All right. Okay, there we go. Reduce this a bit. Which junction do we want to use? Let's just use this junction right over here. Right, this is our junction. Right, now let's see how the current is coming towards the junction and going out of the junction. So we have a current I3 at this location, like so, right? So this branch of the circuit has current I3. So I3 is going to pass through this 1 ohm resistor, is going to pass through this 3 ohm resistor. Now in this branch, we have I2. So I2 is going to pass through this 5 ohm resistor and this 1 ohm resistor. And in this branch, we have I1. So I1 is going to pass through this 8 ohm resistor. So we go to the junction and we use the junction rule. The amount of current entering a junction, in this case is simply I3, right, is equal to the amount that is leaving the junction. And what is leaving the junction? Well, I1 is in that direction, right? like so, and it continues like that, and I2 is in this direction. So we'll put that down as I1 plus I2. This is our first equation. We have formed the first equation using the junction rule. What do we do next? Next up, we use the loop rules. So let's just create two loops and use the loop rule in order to find out what the other two equations are. So we want to come up with three equations over here. So there we go. This is our one loop, right? We are going clockwise. Very important for us to name this loop as well. Let's name the points. Let's name this point, point A, point B, right? The junction, point C, and then D here, right? And then we have E and F. Let's just name each one of these points over here at the edges. Now let's do it for the first loop. The first loop that we have is this loop. It starts from A, goes to B, goes to C, goes to D, and then comes back at A. So we have loop A, B, C, D, and then back to A. Right, back to A. We have to go back to A. We have to go back to the starting point. Right, so we start off. Now this is the direction in which I'm traveling. So let's go. So we're going up, we are going up, but the current is coming down, right? The current is going down. So I know that it's going to have a higher potential over here and a lower potential over here. So essentially, when the direction in which I am traveling, in which you are traveling, is opposite to the direction in which the current is traveling, we'll keep that as positive. So I will write that as a positive. Remember that the potential difference is simply IR or RI, right? Resistance multiplied by current. So what is the potential difference? We are going to keep that as positive. R is 8 resistance value multiplied by the current which is moving through that. That's going to be taken as I1. Right, now let's continue moving. So A to B, B to C, there's no second elements there. Let's go from C to D. So as we are traveling, we see that as we travel across the 5 ohm resistor, we are traveling in the same direction as the current. So we will take that component to be negative. So we'll keep that as negative. Resistance value is 5. What is the current that is moving through it? I2. And then we will go down, and there's another resistor further, and that is a 1 ohm resistor. So resistance value is 1, current value is I2. So 1 I2 or simply I2. Okay, then we continue downwards, and you see we come across a battery. Over here, you're going from the positive to the negative. So you're going from a terminal with a higher potential to a terminal with a lower potential. So we are going to be keeping that as negative. So we go negative 4 is equal to 0. This is our second equation. We can revise it a bit, right? Just get all the like terms, we solve all the like terms. So we just have a few variables there. So we'll have 8I1 minus 6I2. We can take the 4 to the other side, right? So plus 4 over here, plus 4 on that side as well. So we have that as equal to 4. And then what we can do is let's write the equation down for the other loop, right? In this time, we'll look at loop. Let's say again, we're going clockwise in this case. So we will look at loop B. We go to D to C, then we go to E, and then F, and then we end up at D. Make sure that you write the D term right at the end as well. We have to go back to the starting point. So this is the direction in which we are traveling. So let's write the circuit elements just like we did in the first case. So as we are moving, okay, so we're going from a lower to a higher, from a negative to a positive. So we will keep that as plus 4, right? And then as we are going up, you'll see that the current, we are moving up in this case, right? This is the loop we are following. So in this case, we are moving up and the current is moving down. So we'll keep that as positive. So that's going to be positive I2, right? 1 I2 or simply I2. plus, let's again keep on moving up. You have a 5 ohm resistor there. So resistance value is 5I and the value for current is I2. That's the current moving through that resistor. Continue the loop, right? So we come across another circuit element. Now in this branch, you have I3 moving, and this is the direction in which I3 is going to be moving, right? This I've already drawn it previously. So as we are moving in this direction, the I3 current is moving in that direction. So again, we are going to be keeping that as positive, right? So what is the value for resistance? 3. What is the value for current moving through it? We are going to be keeping that as I3. And then again, we continue moving down. What do we have here? We have another resistor, a 1 ohm resistor. Again, as you are going down, but the value or the direction for current is upward. So still keep that as a positive. So positive I3 or 1I3. And then as you go down, you encounter again a battery source, and this is going from the positive terminal to the negative terminal, and you'll keep that as a minus 12. And then don't stop there. We go and we finish off at D. There's no more second element, so that is equal to 0. Then what we can do is we can solve, just bring and add all the like terms together and get the number to the other side. So 4 plus negative 12 is negative 8. So on that side of the equation, I can put it down as positive 8. And over here, we get 6 I2, right? 1, 2 plus 4 I3, right? Plus 4 I3. So we have our 3 equations now. This is equation number 1. This is equation number 2. And this right here is equation number 3. Right? And then we can solve it using a series of processes, substitution, for example, and elimination. Right? All right. So I've shown you how to form these equations, and I'll leave it to you in order to carry out the operations and find out what the values for current is. Right? My purpose here was to just show you how to use the Kirchhoff's laws in order to find out how we can generate different equations. Right. So that is where I will stop, and Mr. Melvin will continue. I'll just quickly stop sharing my screen. There you go. And by the way, let me give you the solutions. The solutions for these ones you'll have try it out by yourselves. Right? Let me just give me 1 minute, and I'll give you the solutions for this one. Right, so we have, if you try it out, your I1 value should be okay, so your I1 value will be equal to 0.85 or so. I2 value should come out as 0.46, and your I3 value should come out as 1.31, right? Amps, amps, amps. Right, so please do try it out and see if you get these values or not. Right, I'm going to leave that to you to try it out. All right, so let me just quickly stop sharing here. Okay, close this. Let's go back. All right. So on my side, I welcome Mr. Melvin. Right. If you have any questions, please type it in the chat box, and Mr. Melvin will give you more details on about how you can contact us if you want to, if you have any questions you want to ask of us. Right. So over to you now, Mr. Melvin.
Thank you, Drishna. So far we have been looking at DC circuits, and Drishna has talked about resistors, and the effects, what effects changes the resistance. Okay? And then we talked about the Kirchhoff's law, which basically is used to analyze a DC circuit. Now, moving forward, what I'm going to be talking about is electromagnetic induction. Okay? And this basically involves talking about Faraday's law and Lenz's law. Okay? What is the difference between the two laws? Right? Now, before we start talking about Faraday's law, we need to understand the difference between the Moto effect and the generator effect. Right? What is the Moto effect and what is the generator effect? Now, when we started with talking about magnetic field, what you when we were talking about magnetic field, along the way, you talked about what happens to a current carrying conductor when it is placed in a region of a magnetic field. Right? What happens to a current carrying conductor when it is placed in a region of magnetic field, and the circuit needs to be complete. Now, when I say circuit needs to be complete, what it means is, right, so we have your conductors, right, we have the one conductor, and then the whole circuit needs to be complete. So that's what basically happens is the current carrying conductor will experience a force. Okay, the current carrying conductor will experience a force. So that is what is known as Moto effect. Now, the generator effect is opposite to what is Moto effect. Now, generator effect is when you place a conductor in a region of magnetic field and you have a complete circuit. Okay, you place a conductor in a region of magnetic field. What actually will happen is this conductor, right, because of the force, right, to move the conductor, it will induce EMF. Okay, it will induce EMF, right, and that EMF will the induced EMF is given by, right, so your capital V is equals to the magnetic field multiplied by the length of the conductor multiplied by the speed of the conductor. Right? So that is the difference between the generator effect and the Moto effect. Right, now, before I move on, can anybody tell me how do you determine the direction with the Moto effect and the generator effect? How do you determine the direction of the conductor? In which direction is it going to move, or in which direction is the force going to be, right? It's going to move. And which direction is the magnetic field, and in which direction is the current? Can anybody tell me how would you determine the direction of each of these? Okay, the force, or the direction of motion, the current, and the direction of the magnetic field. Anyone? Yeah? No? So the answer to that is Fleming's rule. Okay? So you have your Fleming's rule. Now there are two Fleming's rule. One is a Fleming's left-hand rule, and the other one is a Fleming's right-hand rule. Right? So Fleming's left-hand rule is used for the Moto effect. Moto effect is when a conductor is placed in a region of a magnetic field. It will, the current carrying conductor rather, when it is placed in a region of a magnetic field, it will experience force. So the Fleming's left-hand rule, so this is how you are going to go. Okay, 90 degrees here between the thumb and this pointy finger, and then the 90 degrees here between the pointy finger and the middle finger, right? So the thumb points in the direction of the motion, right? The pointing finger points in the direction of a magnetic field, and the middle finger points in the direction of your current. Right? So that is how you determine the direction in which the conductor is going to move, right? When you talk about Moto effect. Now, when you talk about generator effect, and what is generator effect? Generator effect is when a moving conductor is placed in a magnetic field, you have your induced EMF, okay, and which basically, if the circuit is complete, it will produce current, right? So this is how a generator works, right? Hydropower generators and all those stuff, that is how it works. Now, for a generator effect, what we have is the Fleming's right-hand rule. Okay, so this is your left-hand rule, Fleming's left-hand rule is used for your motor effect, and your Fleming's right-hand rule is used for your generator effect, which states that your thumb, again, everything needs to be in 90 degrees, right? So your pointing finger and your middle finger, the angle between them is 90 degrees, and the thumb and that the pointing finger, the angle between them is 90 degrees as well. So these points in the thumb always points in the direction of the magnetic field, sorry, the direction of your motion, okay, in which direction is the conductor moving, and the pointing finger points in the direction of your magnetic field, and your middle finger points in the direction of your current, right? So this is a generator effect, motor effect, right? Motor effect is used for electrical energy to mechanical energy, right? And the generator effect is used for your mechanical energy to electrical energy. So these are things which you must have done when you talk about magnetic field. Okay, you briefly talk about that. Now, the generator effect is basically a foundation for electromagnetic induction. Okay, electromagnetic induction. Right. So what happens in electromagnetic induction is if you have a conductor, if you have a conductor and it moves, okay, let me share my screen with you. Okay, hopefully you can see the screen, right? So there you go. I'm talking about electromagnetic induction. And when we talk about electromagnetic induction, we are going to dive right into Faraday's law. Okay, so Faraday's law, basically what resulted in the Faraday's law was that it was observed that when you have a when you have a magnet, okay, such as this, and this is a coil of wire. Now, when this magnet is either moved into the coil of wire or out of the coil of wire, so when it is moving, what basically happens is there is a deflection in the ammeter, or right, the deflection in your ammeter. Okay, you can use a galvanometer as well, right? So if you have a ammeter, there is going to be a deflection when you are going to move this magnetic field into the loop, right? So this is what is an example of a generator effect, right? This is the force moving your conductor into the coil of wire. Now, if this conductor or this magnet does not move, okay, this is not moving, what basically will happen is there's going to be no deflection in the ammeter. When the magnet is held stationary, there is no induced current in the loop, right? Even when the magnet is inside the loop. So regardless whether the magnet is inside the loop or outside the loop or on the left hand side, regardless of the position of your magnet, right? Once the magnet is stationary, you are not going to have any, sorry about that, you are not going to have any induced current, right? But when the magnet is moving, you are going to have an induced current. Okay, so this is what is known as electromagnetic induction, okay, which was observed by Faraday. Okay, now this is right. So this is what was used to understand or define Faraday's law. Now the experiment itself, what it Faraday's experiment, how it was built up was, so you have your coil of wire, so you have your magnet, and then you have your primary circuit, which is a closed circuit connected to a battery, and then you have a secondary coil, right, which is wound around this magnet, and then it is connected to an ammeter, right? So what happens? There is no battery connected to the ammeter. Okay, so there is no battery present in the secondary coil. Okay, what is present there is just the ammeter. What we are going to be looking at, what I understand here is when the circuit closes, what happens when the circuit closes? There is going to be an induced current in the EMF, in the ammeter, right? So then that EMF induced in the secondary, oops, sorry about that. right? So the EMF induced in the secondary circuit is caused by the changing magnetic field through the secondary coil, right? So you have a changing magnetic field. The reason why there is a changing magnetic field is because of the primary and the secondary coils. Okay, the number of turns of wire around the primary and secondary coil. Now, what is the changing magnetic field? Okay, so magnetic field and the changing magnetic field basically creates a flux. Right, so flux basically refers to the amount of magnetic field that passes through a area A. Okay, so right, so flux refers to your amount of magnetic field passing through an area A. So if this is your length, right, and that is your width, right? So your length times width, that becomes your area, and the amount of magnetic field passing through that is your flux, right? So changing magnetic field through the secondary coil. So what Faraday's the findings of the experiment was that at the instant the switch is closed, the ammeter changes from 0 in one direction and then returns to 0. Right, and when the switch is opened, the ammeter changes in the opposite direction and then returns to 0. So the ammeter reads 0 when there is a steady current. Okay, so this is the example what we observed or what we talked about in the generator effect. Right, right. So if not the generator effect, sorry, electromagnetic induction. Right, when the magnet is moving, the ammeter is going to deflect, but when the magnet is stationary, there is going to be no deflection in the ammeter. So that was what was the findings of the Faraday's experiment. Okay, and this is what was seen. So now the conclusion for Faraday's experiment conclusion is that when an electric current can be induced in a loop, yes, when an electric current can be induced in a loop by changing the magnetic field. Okay, and this would be the current in the secondary circuit of this experimental setup. Changing the magnetic field. And how do you change the magnetic field? Yeah, remember Fleming's right-hand rule, right? You have your magnetic field, and if you change the current, how do you change the current? Is with the number of loops, right? The difference between the number of number of loops in the primary and the secondary coil. So that's what changes the magnetic field. Right, so, and that changes the magnetic field, and the induced current exists only while the magnetic field through the loop is changing. Right, so what you basically have is an induced EMF is produced in the loop by the changing magnetic field. Okay, and so this is what is known as the Faraday's law. Okay, when there's a changing magnetic field, you have an induced EMF. Okay, when you have a changing magnetic field. Now, whenever there is a change in magnetic field, right? Now, so the EMF induced in a circuit is directly proportional to the time of rate of change of the magnetic flux through the circuit. So what it basically means is the changing magnetic field. Right now, the magnetic field can only be changed if your area changes or the flux changes, right? And the flux is given by the magnetic field multiplied by your area. Okay, the magnetic flux is given by the magnetic field multiplied by the area of the loop which is in the magnetic field. So when this magnetic field changes or the area changes, what will happen is there's going to be a change in the magnetic flux. Right, so the rate of change, right? The rate. So whenever you talk about the rate, it is always written as differentiating it with respect to time. Or you can just basically put it as change in magnetic flux divided by change in time. Okay, and change is always given as your final minus initial divided by change in time. So your final time minus your initial time. Right, so this is your change in the magnetic flux. Right, so this is what is represented by the rate of change of the magnetic flux. D phi by dt is given as the final magnetic flux minus the initial magnetic flux divided by the final time minus the initial time. Okay, the difference between them, and then you can have a negative sign. Huh? The negative sign we're going to talk about in a while. What is the purpose of that negative sign over there? Okay, now. So that is what is the induced EMF in a circuit. Okay, so if there's a circuit and there's a changing magnetic flux, right? So the induced EMF is equal to the rate of change of the magnetic flux through the circuit. Now, if you have n loops of wire, okay, if you have n loops of wire, okay, say suppose so this is your magnet here, and then you have your another magnet here, you have your north pole, the south pole, right? So magnetic field moves in that direction, right? So let's draw like that. Okay, so here this represents your area. Now at the moment, okay, at the moment what happens is, can you see the magnetic field does not cut through the loop of wire, does not cut through the loop of wire. So that what it basically indicates is there's going to be no change in magnetic field, sorry, magnetic flux. So at this point in time, what we have is the induced EMF is equal to 0. But as this tends, so what will happen is this is going to move, right, rotate, and there's going to be magnetic field passing through the loop of wire. Okay, and that changes the magnetic flux, right? Because it is rotating. So anything which is moving, rate of change. Okay, so anything which is moving, it is with respect to time. Okay, and because you see as it moves, because as it moves, the area through which the magnetic field passes changes. Okay, because if you let it be here, okay, if you view from here, what happens? This is going to be your this is what you will view, and the magnetic field does not pass through that. But if it rotates through 45 degrees, what happens is this is what is okay. So there you have your magnetic field passing through that. But and if it rotates through 90 degrees, then you have your maximum magnetic field passing through the loop of wire. Right? So the change in magnetic flux. Why? Because the area changes. Right? Here the area through which the magnetic field passing is 0. Here the area is that area over there, and here we have the total area of the loop of wire. Now, if there is n number of loops, okay, for this wire wound around the magnetic field, then the induced EMF will be equal to the whole thing, the rate of change of magnetic flux through this loop of wire multiplied by n. Okay. Right. So now, so that is on the change in magnetic flux. Now, if we look at this, okay. Now, if you have a magnetic, sorry, a loop of wire as such, okay, and that is your magnetic field which passes through the loop of wire. Right now, the maximum flux is always when the magnetic field passes through 90 degrees. Okay? So this is what is going to give you the maximum magnetic flux. So in order to calculate the magnetic flux in this case, which is equal to PA, right? So you use this formula only when your magnetic field is perpendicular to the loop of wire. Now, if the magnetic field is at an angle as such, theta, now what in this case, the magnetic flux would be given by, now, so magnetic flux is this. This is the magnetic flux which we are going to be using. Remember, the perpendicular to the magnetic field. So if you use that, and that is your magnetic field, the magnetic field in the x direction basically will be equal to B cos theta. Right? So your magnetic flux therefore is equal to B A cos theta. Right? So and the induced EMF in this case basically will be equal to negative N T. What is your phi in this? The magnetic flux would be equal to B A cos theta divided by dt. Okay. Now, so let's look at let's look at how can you ways of inducing an EMF. Okay, how can you change or induce an EMF? Right. Now, there are a number of ways in which you can change the induced EMF. Okay, the first being the magnitude of the magnetic field. Okay, let's look at the formula for the induced EMF. Okay, okay, the EMF is equal to negative N T BA cos theta with respect to time. So the magnitude of the magnetic field can change with time. Okay. The area enclosed by the loop can change with time. So if you change with the magnitude of the magnetic field, if you change the area of the loop with respect to time, okay, or you change the angle between the magnetic field and the loop of wire, this will bring about changes in the induced EMF or any combination of the above. Okay, any combination meaning changing in the magnetic field, changing in the area, changing in the angle between the magnetic field and the coil of wire. Okay, so that is an electromagnetic induction. Okay, basically Faraday's law. Okay, what causes the induced EMF in a magnetic field? Now, so now it is time to look at our look at some questions. Okay, let's look at some questions. The first being is a multiple choice question. Now the question says, which of the one of the following laws of electromagnetism does not give the direction of a magnetic field? Okay, I want you to type in your answers within the chat box. I will give you 10 seconds or 15 seconds to answer that. Okay, which your time has already started. Which one of the following laws of electromagnetism does not give the direction of a magnetic field? Okay, time's up. Okay, so A says right hand thumb rule. Okay, B says so right hand thumb rule. This is what a right hand thumb rule states. Okay, the finger scale in the direction of the magnetic field, and the thumb points in the direction of your current. Okay, so that is what is right hand thumb rule. Fleming's left hand rule, we have just looked at that. Okay, that is for the motor effect. And then you have Fleming's right hand rule, which talks about the generator effect. And then the pointy finger points in the direction of the magnetic field. So all three, A, B, and C, does give you the direction of the magnetic field. The only law which does not give you the direction of magnetic field is Faraday's law of electromagnetic induction. And basically, what does Faraday's law give you? Okay, Faraday's law is used to determine the induced EMF. Okay, when there is a changing magnetic field within through a changing magnetic field. Okay. Now, let's look at another example or exercise. The next question. Okay. It says that a small rectangular coil of wire, coil contains 350 turns of wire. Okay, so the longer sides are 3.5 centimeter and the shorter sides are 1.4 centimeter. Okay, and then the coil is held between the poles of a large magnet so that the coil can rotate about an axis through its center. So this is the axis of rotation, and this is how it is going to be rotated. Okay, let's assume that this is how it is going to be rotated. Now, the magnet produces a uniform magnetic field of flux density 80 milliteslas. Okay, the unit for flux density, the magnetic field, remember, It's Teslas, so milliteslas, 80 milliteslas between its poles. So if this is your north pole, that is your south pole. The flux density between that is 80 millitesla. The coil is positioned horizontally, right? So once the coil is positioned horizontally, okay, if the coil is positioned horizontally, what basically happens is there is no magnetic field passing through the coil. So if you have a magnetic field going through like that, okay, and this is your coil, right? So that is your magnetic field. Now the coil is positioned horizontally. Now what happens is there is no magnetic field passing through the loop of wire as such. So when there is no magnetic field passing through the loop of wire, there is going to be no change in magnetic field. Now, what happens is the question indicates is, or the question reads on as to that, right? And then the coil, what happens basically, it is turned through an angle of 40 degrees in a time of 0.18 seconds. Right? So if you have as such, and in 0.18 seconds, the coil has moved as such, okay, with an angle of 40 degrees. Now, there's going to be some magnetic field passing through the area, okay, passing through the coil. And then, so initially it was as such, and then now it is as such. So what happens? There's going to be a change in the magnetic flux. What was the initial magnetic flux? Okay, initial magnetic flux, right? So we'll talk about that. So, and then initial magnetic flux, sorry, it says calculate the magnitude of the average EMF induced in the coil. Now, whenever you are answering any physics question, okay, the first step, okay, or the first two steps which you should practice is always write down the information. Okay, uh, write down the information which has been provided in the question. Okay, and if you are not sure of what is happening, always illustrate. Right, try to draw up what is happening in the question, because once you do that, okay, you draw what is happening in the question. Now in this question, you see that what is happening in the question, there is an illustration provided. Okay, but if there is no illustration provided, try to draw or illustrate what is happening in the question, because once you try to illustrate, it helps you understanding what is happening. Okay, so the first two steps, okay, most important step is write down the information provided in the question, illustrate what is happening. Okay, so let's look at the question itself. Okay, so you have your coil of wire, right? You have your coil of wire. So you have your length as given as, sorry. Okay, so your length is given as 3.5 centimeter, and your width is given as, so your length is given as 3.5 centimeter. So let's write it down, 3.5 times 10 to the power negative 2 meters. And your width, or the shorter side, is given as 1.4 times 10 to the power negative 2 meters. Right? Now, moving on, what else is given is there is your N, the number of turns, which is given as 350 turns. Okay. And what else is given is that the magnetic field is 80 milliteslas. Okay, magnetic field is equal to 80 milliteslas. Okay, and then initially what happened was that the loop was horizontal. There was no magnetic flux through the coil of wire. And then in time of 0.18 seconds, the magnetic flux rotated 40 degrees. And then you are supposed to be calculating your EMF. Right? So your EMF, let's write down the formula. Now, what is your formula? So EMF is equal to negative N d phi by dt. Okay, EMF is equal to negative N d phi by dt. Now the change in magnetic flux is always equal to final magnetic flux minus initial magnetic flux. Right? Now, so in this case, it can be given as N d into dA cos theta by dt. Now, why I can do that is because the initial magnetic flux is equals to 0. Okay, the initial magnetic flux is 0. Now substituting into this formula, N, you have your N is given as 350. Okay, and then D basically, right? So differentiate, so or change, right? So you B magnetic field 80 times 10 to the power negative 3. Area, you have your it's a rectangle, so 3.5 times 10 to the power negative 2 times 1.4 times 10 to the power negative 2. Okay, and then cos theta multiplied by, I'll put here, cos of 40 degrees, and the whole thing divided by time, which is 0.18 seconds. Right, so in this case, if you can calculate that, what is your answer to that? Okay. And the answer to that is 0.058, or you can just put it as 58 millivolts. So change in magnetic flux. Now, so the next thing which we are going to look at is, that is all on electromagnetic induction or Faraday's law. Okay, Faraday's law basically talks about the changing magnetic, the EMF induced when there's a change in magnetic flux. Now, extension to Faraday's law, okay, is what is we right. So if we have your Faraday's law, but there's an extension to Faraday's law which is known as the Lenz's law. Right, so your Faraday's law indicates that the induced EMF and the change in flux have opposite algebraic signs. Remember, E is equal to negative N d phi by dt. So this here, the negative sign indicates that the change in magnetic flux and the induced EMF, they are in the opposite direction. Okay, that is what is the purpose of the negative sign. Now, this has a physical interpretation that has come to be known as your Lenz's law. The Lenz's law, which states that the induced current in a loop is in the direction that creates a magnetic field that opposes the change in the magnetic flux. Okay, let's look at that. So you have your induced current in a loop. Okay, and that induced current is in a direction that creates a magnetic field. So if you have your induced EMF, right? So if there's a change in magnetic flux, what will happen is there's going to be an induced EMF. Now, if the circuit is closed, the induced EMF will produce an induced current. Okay, the induced EMF will produce an induced current. Now, from the the right-hand Fleming's rule, what it indicates is that when there is a current, okay, and there is a conductor moving through a magnetic field, what will happen is there is going to be there's a conductor moving, right? There is going to be an induced, so it will create a magnetic field given as such, right? And this magnetic field, which is created by the induced current due to the changing magnetic flux, right? The induced current, so you have your motion, current, magnetic field. Now this current is because there was an induced EMF due to a changing magnetic field. Good. Now, so the induced current, basically what it does, it produces a magnetic field or creates a magnetic field. And this magnetic field is going to oppose, okay, this magnetic field which has been created by the induced current is going to oppose the change in magnetic flux. Okay, remember this magnetic flux, okay, so this magnetic field which has been created due to the change induced current is going to oppose this change in magnetic flux through the area, and that is what is known as your Lenz's law. Okay, now so Lenz's law, let's look at Lenz's law in a bit detail. right? What it says that the conducting bar in the next slide, which I'll show you, it slides onto the two fixed conducting rails. Okay, so you have your conducting bar. This is your conducting bar, which slides onto the conducting rail. Now, the magnetic flux due to the external magnetic field through the enclosed area increases with time. Okay, so the magnetic flux within the enclosed area is going to increase with respect to time. Why? Because this is moving in that direction. Oops. Right? And then the induced current must produce a magnetic field out of the page. Right? So what will happen is the induced current which flows is going to produce a magnetic field which opposes this magnetic field. Now this magnetic field, the initial magnetic field is into the page. So the induced current, which is right because of this moving conductor, okay, the induced current because of the moving conductor is going to create a magnetic field which opposes this magnetic field, and that magnetic field is going to be in this case out of the page. Okay. So that is on Lenz's law. Any question on that? Okay. Now before, so that is on Faraday's law and Lenz's law. Okay, Faraday's law basically talks about the induced EMF when there's a changing magnetic flux, okay, with respect to time. And Lenz's law talks about how the induced EMF, which induces a current, and that current induces a magnetic field which opposes the magnetic field which brought about the change in the magnetic flux. Right? You have your so everything is being tied together with the Lenz's law. Okay, you have your Fleming's right-hand rule, which is the generator effect. Okay, and then you have your current, magnetic field, and the motion of the conductor. Right. So according to Faraday's law, when there is a moving conductor, right, the flux passing through the moving conductor is going to induce an EMF, and that induced EMF is going to induce a current, and the induced current, based on this, okay, induced current is going to create a magnetic field, and this magnetic field will oppose the initial magnetic field which brought about the change in the magnetic flux, or which brought about the induction of the EMF. Right, so let's look at the question and then we will finish off with this slide of talking about Lenz's law. Okay, let's look at this. So the exercise states that a small 10 mm diameter permanent magnet, okay, 10 mm diameter permanent magnet, remember this talks about the diameter, produces a magnetic field of 100 millitesla. Now the field drops away rapidly with distance and is negligible, right, for more than 1 mm from the surface. Right? So the field drops away rapidly with distance and is negligible for more than 1 mm from the surface. Now, if this magnet moves at a speed of 1 meter per second through a 110 coil of length 1 mm and diameter just larger than the magnet, the diameter is just larger than the magnet, what is the EMF induced? In this case, let's look at okay, part A. So let's write down the information. So the diameter of the loop is just larger than the diameter of the magnet. So we can put the diameter of the magnet as 10 mm. Remember, it talks about the diameter of the, so the diameter of the loop, so the loop is in this case going to be a radius, sorry, the circle. So in order to find the area of a circle, we always talk about the radius. The radius in this case is going to be 5 times 10 to the power negative 3 meters. What else do we have is that the magnetic field is 100 milliteslas. Okay, so the magnetic field is equal to 100 millitesla. Right, and then it says that n is equal to 100, right? N is equal to 100. Okay, and then what other information do we have? We have the speed there and the length of the coil. which is 1 mm. Right? The speed with which the magnet moves through the coil is 1 meters per second. So what we have is, if you try to illustrate, okay, so we have something like that. Okay, you have your 100 coils. Okay, and the distance, that distance is 1 mm. And if that is the magnet, what happens is that magnet is going to move through that coil with a speed of 1 meter per second. Right? Now, so you have a speed. Now, we are supposed to be calculating the EMF. Okay, the EMF is given by negative N d phi by dt. In this case, you see that the magnetic field is perpendicular to the area of the loop. So we can basically put it as negative N PA divided by time. Right. Now you have your N, which is 100. You have your magnetic field, which is 100 milliteslas. You can calculate the area. Okay, so the area will be given as pi r squared. Now, what we do not have is the time. Right? So how do we calculate what is the time? Yeah, how do we calculate what is the time? Right? So what we have is your magnetic field. Okay, and that is your length. Oh, sorry, the length of the coil, and this is your magnet which moves through the coil. Now, the change in magnetic flux will only be equal to, okay, will be equal to when this magnet is inside the magnetic field. Okay, when the magnet is inside the magnetic field. So as soon as it enters, right, and then as soon as it exits, so that is when there is going to be a change in the magnetic flux. Right? Yes, right. Remember when we started talking about the electromagnetic induction, right? The build up to Faraday's law, right? The change or the induced current when we talked about the ammeter was only happening when the magnet was moving. If the magnet was stationary, there was no induced current. In this case, the same thing. Okay, the induced EMF is only when the magnet moves through the magnet moves through the coil of wire. Okay, the magnet moves through the coil of the wire. So in this case, would be that. Right? And the time for which the magnet passes through this length of wire, you can calculate that as we have your speed, you have your length or the distance of that. So you can have your speed is equal to distance divided by time. Or time would basically be equal to distance divided by your speed. And your distance is 1 mm or 1 times 10 to the power negative 3 divided by 1 meters per second. Therefore, the time the time for which there was an induced EMF in this coil was 1 times 10 to the power negative 3 seconds. Okay, substituting all the values into this, okay, you should be able to get your answer as 0.78 volts. Any questions with this? Understanding what is happening, okay, or what understanding what is happening when they right when or what right what causes an induced EMF within the magnetic within the coil of wire. Right? Now let's look at exercise part B to this question. Part B says if the magnet is dropped north pole first, okay, if the magnet is dropped north pole first, so this is going to be your north pole and that is going to be your south pole. Yeah, let's just draw that again. So that is your coil of wire. Okay, and then that is your north pole, the magnet, and that is your south pole. If the magnet is dropped north pole first, okay, through the coil of wire. Now the question asks what direction, clockwise or counterclockwise, will the current first flow in the coil? Okay, what direction, clockwise or counterclockwise, will the current first flow in the coil? Now, to answer this, what we are going to do is we are going to look at Lenz's law. Okay, because we are talking about the induced current. Now, as soon as the magnet is dropped through this, what will happen is there is going to be a magnetic field, right, which passes through that. Now, in order to determine the direction of the current or the induced EMF, we can use right hand grip rule. Okay, we can use the right hand grip rule, which indicates that this is points in the direction of the magnetic field. And this points in the direction of the current. Okay, so when you do that, yeah, right. So when you do that, what we have is your magnetic field rotates in the clockwise direction. Okay, your magnetic field rotates in the clockwise direction. According to Lenz's law, the current induced opposes the direction of the magnetic field. So in this case, the current is going to be in the counterclockwise direction. Okay, in this case, the current is going to be induced in the counterclockwise direction. Okay, so that is the solution for part B. Sorry. Which is there. Okay. What direction will the current first flow in the coil? Okay, the answer to that is the current will first flow in the counterclockwise, because according to Lenz's law, the current is going to oppose. Okay. So that's all on Faraday's law and Lenz's law. So you can write down our email addresses. So if you have any questions, you can always email us with the questions, and we would be able to help you out with your questions. Okay, and if you have any difficulty in understanding any concept, you can always email us. Okay, and then we would help you in understanding what the concept better. Right? That is our email addresses. Drishna. So you have drishnac@unipg.ac.fj, and you have Melvin N@unipg.ac.fj. Thank you. Anybody has any questions? Krishna, would you like to? Sorry.
Right. So I'll just like to thank all the students, right? Thank you for attending the tutorial. If you do have questions like Mr. Melvin has mentioned, please do email us those, and we will reach out and try to help you. Whichever manner is going to be convenient for both you and us as well. So please feel free to email us if you need any extra help. We will be able to provide it. And I know we exceeded our time a little bit, so thank you for bearing with us. The other thing that I wanted to mention is, yes, all the best for your final examinations, and revise well, and do let us know if we can help out in any way. Thank you all for attending. So with those words, I will close this tutorial, right? And I look forward to queries, in fact, from you if you have any. Thank you all.